let's try to carry out this procedure for sigma algebras and see what happens. So the context is the same. X is any set, and F is any collection of subsets of X. And we're trying to describe the sigma algebra on X generated by F. Here is the procedure we carried out in the previous video for successfully constructing the algebra of sets, not sigma algebra, generated by F. What do I need to change? So the only difference between a sigma algebra and an algebra of sets is that the sigma algebra is closed under countable unions. Sorry, wrong emphasis there. Is that that the sigma algebra is closed under countable unions. Okay, so what do I need to change here? How about I start with F. I do need to throw in complements. Sigma algebra should be closed under complements. Now, if I keep this finite, that would be a bad idea, because ultimately I'm going to want to throw in countable unions, right? Ultimately I'll throw in countable unions of things back there. And if I take a countable union of things in F2 or in F1, and I take its complement will be a countable intersection, right? Using De Morgan's law. So I need to say countable in both places, for sure. Definitely I need to say countable in both places, if this even has any chance of working. Now my question is F3, so here's the big question, is F3 equal to the sigma algebra on X generated by F? Is it? Well, by the same argument as before, which I left here, when we were talking about is F3, when we were taking only finite intersections and finite unions, and we're talking about this, we had this inclusion, right? For the same reason, we definitely have that inclusion. That part is easy. We definitely have this inclusion. That's because anything in F3 definitely has to be in any sigma algebra that contains F, right? Simply because sigma algebra that contain F are closed under complements, countable intersections, countable unions. And they have to contain these two sets here. So the question is, did we get all of them? That's the real question. Did we get all of them? And the answer in the end is going to be no, not even close, at least in general. Okay, so for the same reason as before, what it comes down to, what this inclusion comes down to, is checking, basically, here's our big question, is F3 a sigma algebra on X? If it is a sigma algebra on X, then it definitely contains as a subset what is by definition the smallest sigma algebra on X that contains F. So this does contain F, since F is inside F1, is inside F2, is inside F3. So it just remains to verify that this is a sigma algebra on X. So what do we need to check? That the empty set is in there. No problem. We added it in at the first step. That's easy. Needs to be closed under countable union. Duh. It's at the last step we threw in all countable unions of things from the previous step. If you take a countable union of countable unions of things, then that is a countable union. Okay, I should not have said duh. That's not actually that obvious necessarily. A countable union of countable unions is a countable union, but it is. And this is one of those things you study in set theory. So just in case that makes you feel weird that a countable union of countable unions is a countable union, here's a way of thinking about it, or at least reducing it to other things that might also make us feel a little weird. So imagine that you have one countable union, and the union of the A1s, A11, A12, A13, etc., countably infinite union. And then you have another one, A21, A22, etc. And then you have countably many of those actually. So this is a countable union, this is a countable union, etc. And then you take a countable union, so there's countably infinitely many of these rows here. So it looks like we have countably many columns, countably many rows. This looks like each position in this looks like a grid in which each position can be labeled by an element of this Cartesian product, right? And is this Cartesian product a countable set? Yes, in fact, this is one of the facts that is used to prove that the rationals are countable, right? Like trying to write fractions in all these places, like 1 over 1 here, 1 over 2, 1 over 3, 2 over 1, 2 over 2, 2 over 3, with repeats maybe, and then you go down kind of trying to list them all in one linear sequence in order to prove that there are countably many rationals. So a countable union of countable unions is a countable union, and that should only make you feel as weird as you feel about the rationals being countable. Okay, back to the main topic. Sorry about that. Here. So definitely, so we were checking, is F3 a sigma algebra? Definitely, it is closed under countable unions. All that's left is check that it's closed under complements. So is F3 closed under complements? Well, do you remember what we did in the algebra rather than sigma algebra case for showing closure under complements? This is what we did. We started with something in F3. This was the algebra rather than sigma algebra version. And we ended up showing that it's that showing closure under complements reduces to showing closure under finite intersections. So that's because when we took the complement of a finite union of a finite intersection of things from F1, that ended up being the finite intersection of a finite union of things from F1. And so this union, finite union, was always in F2. So this was an intersection of things in this finite union here was in F3, and so this was an intersection of things in F3. So we reduced the problem to showing closure under intersection. We can do the same thing here, in our situation here, where we have replaced finite by countable. We'll start with a set A, which is in F3. Then we will write it as a countable union of a countable intersection. So replace the n here by possibly infinity, by which I mean a countable union. And replace this by infinity, by which I mean a countable intersection. Then De Morgan's law holds regardless of cardinalities. De Morgan's law is a very universal thing. So this, you get this, but with infinities here, right? And again, these are complements of things in F1, so they are in F1. Therefore, they are in F2. Therefore, this is always in F3 because it's a union of things in F2, countable union of things in F2. So it's something in F3. And so we've reduced the problem to showing that F3 is closed under countable intersections. Sorry, here. So the question is F3 is sigma algebra comes down to this reduces to this, which reduces to the question, is F3, is it closed under countable intersection? Now, there's one thing that was very nice that was available to us when we were doing the finite version of this with algebras of sets, which was that when we wanted to check closure under finite intersection, it was enough to consider just two sets and intersect two sets, because then you can use induction to get any finite intersection. Here, in the current context, that doesn't work, right? Induction from finite intersections is not going to get us up to countable intersections. That's not how induction works. So we have to deal with the full problem here. So let's try it. It feels like, to me at first at least, it feels like I should be able to just mimic the steps here and it should work. So what part of the steps here is going to fail? Look what I've written. Okay. Assume that I have a countable collection A1, A2, A3, etc. of things in F3. Now, let's intersect them and see if we can prove that that's something in F3. Each one of these is since it's in F3, to be in F3 is to be a countable union of things in F2. So each one of these can be written as a countable union. Each AI is, okay, I paused for a second to try to find a good notation for this, and I have decided that I'm going to use the index k here so that I can use I similarly to how I was using before. So each ak, for all natural numbers k, is going to be the union of aki's, where I runs from 1, where, let me put it this way, where I is running over the natural numbers. So this is a sequence in F3, and each one is the union of a sequence of things in F1. So where these are in F1, F2 for all I in it. All right, now I want to intersect these A's. So this is analogous to over here when I had written my two A's. Well, now I have countably many A's, but back here I had written my two A's each as a finite union, and then I intersected the finite unions. And then I had this nice distributivity thing going on. So maybe I'll get something analogous. So now the intersection from running over all natural numbers k of the AKs, my goal is to show that this is in F3. If I do that, I will be done. Then I will know that F3 is a sigma algebra on X. So this is the intersection. My intersection symbols get larger and larger as the drama and tension increases of the union I and N. So we do get a kind of distributivity here. So here we're at this step, sort of like this step, where we applied the distributivity of intersection over union, kind of like treating intersection as multiplication and treating union as addition, or pretending for the sake of thinking about how this would work. Here, this is that step. So there is a similar kind of thing that can work in order to interchange whether I'm doing union first or intersection first. So let's see how to write this. This will be the union of, okay, so I'm doing something, I'm trying to do something analogous to this. So here I took the union of each possible intersection where I take something from here and something from here. So each item in this big union here is an intersection where I took one of the things from this union and one of the things from this union. So there were n times m possibilities. So here, this is going to be a big union where each item is going to take one thing from the k equals 1 position, and then one thing from the k equals 2 position, one thing from the k equals 3 position, and so on. So kind of like this. A, from the k equals 1 position, I take one thing. Let me call that thing I sub 1. Then from the k equals 2 position, I take one thing. Let's call that I sub 2. And so on. And I need to do that forever. So what is this union over? It's over all the different choices of things that I take from, it's all the different choices of I1 and all the different choices of I2 and so on. So here's one way to put it, I guess. for all the I1s, natural numbers, all the I2s, all the I3s, and so on. Okay, there's definitely a better way to write this. So if I think of the i's as kind of, let me put it this way. Let's think of this as I of 1, thinking of I as a function, I of 2, I of 3, etc. Then this is basically running over all possible functions I from natural numbers to natural numbers. So this is a union. Let's make a giant union symbol. A union over all possible functions from n to n of intersections. Now this is indexed by the k up here. And what's down here is I of k. Now that is definitely a lot of things that I'm unioning here, right? That's a lot of things. There are a lot of functions from n to n. But that's not surprising. I mean, that's what happened before, right? Here I have A being the union of just n things, and A1 being the union of n things, A2 being the union of m things, and then when I intersected them, I got a much larger union, the union of n times m things. And if I weren't relying on the fact that induction helps me, then here, instead of having just A1 and A2, I would have had a finite list, A1, A2, A3, etc., up to a certain point, and it stops. Then here I would have had, you know, n times m times l times whatever, but it would be some finite number, but it would be large. So I'm not surprised that there's a lot of things showing up in this union after I distribute like this. But is this a countable union? At least before, when we reached this stage, this was a countable union. Oh, sorry, a finite union, which is what we needed at this stage. It was large, but finite. But is this a countable union? No. And there are a couple of ways to see that it's not a countable union. Basically the collection, so this union is indexed over all possible functions from n to n. The collection of functions from n to n is not a countable set. Functions from n to n are like sequences of natural numbers, right? That's not a countable set. So one way to prove that it's not a countable set is the standard Cantor diagonal argument thing that you've probably seen in various places. Another way to just make it believable to you in a real analysis context is that a sequence of natural numbers, here the i's are sequences of natural numbers. A sequence of natural numbers you can think of as the digits in a decimal expansion for a real number, a positive real number, I guess. And there are certainly uncountably many of those positive real numbers. So this is not a countable union. And that's the difficulty. So I hope that this helps you appreciate the extreme change that occurs when you replace the word finite here by countable. We are doing something very different when we look at sigma algebras versus just algebras of sets. And sigma algebra generation, trying to generate a sigma algebra from a set, it's a very hard thing to actually describe. Just doing this is not sufficient. Okay, well, you might still try something else here. So throwing in countable unions of things in F2 and getting F3, the problem was that put us in a position where it's not closed under countable intersection, right? That's what we just ran into trouble with, trying to show that it's closed under countable intersection. It's not necessarily. So how about we throw in countable intersections again? Then it's closed under countable intersection. In F3, and that will give us a new class of sets, which we can call F4. So that's good. the problem, same sort of argument as before, but with intersections flipped with unions, this is not necessarily going to end up being closed under countable unions. So what would you do next? Throw in countable unions of things in F4 and get F5. But now it might not be closed under countable intersections. So let's throw in countable intersections of things in F5 and build F6. But now it might not be closed under countable unions. Okay, so let's do this forever. Let's keep doing this, trying to close it under countable intersections, under countable unions, and hopefully complements will get covered along the way thanks to the duality of things or whatever. But once you do this, I mean, you're seeing that there's problems at every stage. You might think, I certainly might think, that if you just take the union of all of these classes of sets, sort of like the limit of this operation, but it's not a calculus limit, it's just take the union of all of these classes of sets that you build up. So F5, F6, F7, F8, and so on. Union all of them. Each one is bigger than the previous, right? Keep enlarging. Do we finally get the entire sigma algebra on X generated by F? Still not necessarily. So even if you take countable unions of countable intersections of countable unions of countable and allow yourself to do that any finite number of times, you still might not get the full sigma algebra on X generated by F. Of course, I say might not. It might work still. So it's not like we proved that if you just carry out up to this step and get F3, it's not like we proved that it's not a sigma algebra. We just failed to prove that it is a sigma algebra. We failed to prove that it is closed under countable intersection. But it might still work out for specific sets F. The problem is there exist counterexamples where even if you build up forever and do this forever, and then union all of the forever, it still doesn't work. The problem is these are not actually pathological examples where it doesn't, where this attempt at a constructive description fails. It's not for crazy Fs here. It actually happens for really normal ones that we encounter in everyday measure theory. So this is the reality of generating a sigma algebra. One thing I'd like to compare with is the idea of a topology and trying to generate a topology out of the set. So sigma algebra is very similar in the form of the definition, at least, to topology. We end up with a very different idea, but if you just stare at the definition, topology also needs to have the empty set and the full set, which you need to explicitly say. Topology doesn't have to be closed under complements, but it has to be closed under finite intersections and then not only countable, but arbitrary unions. So even non-countable unions. If you take a set and try to use it to generate a topology, you can do something like what we started to do here, where you start with your set, throw in the empty set and the full space, and then don't throw in complements, because topology doesn't want you to be closed under complements necessarily, but throw in finite intersections. Then you would create what is called a basis for a topology. Then to continue generating a full topology, you throw in arbitrary unions. So you take arbitrary unions of finite intersections of things from your original set. When you do this, and that works, that will end up generating a topology. So topology is much friendlier in terms of being able to constructively describe what you're generating. It basically stops at F3 and just don't do anything with complements. When you do this, by the way, the generating set that you start with is called a sub-basis in topology. And the set that you get after you throw in finite intersections, the F2, would be called a basis for a topology. So I hope that you're getting the lesson from this, that sigma algebra generating from a set of subsets of a set, that sigma algebra generation is really freaking weird. But there are some less crazy situations. If F is just has one set, so say it's just a singleton. So A is just one subset of X, and you just want to generate using one set. That's not so crazy. And that means, and actually, if you start with a sigma algebra and you try to adjoin one new thing, so start with a sigma algebra and add in one new thing, and then look at the sigma algebra on X generated by a known sigma algebra that you're starting with, and then just one new set. So you might call this adjoining a new set to a sigma algebra and looking at the generated sigma algebra. This is not so crazy. This is not that crazy. You can constructively describe the elements of this. So I will just point you to example 127 in the text to see how to deal with a situation like this. And since this helps you handle adjoining one element, that means it helps you handle adjoining any finite number of elements by induction.